S-Chan presents Educational Video Lectures. Difficult concepts made easy. Study anywhere, anytime.
Welcome to S-Chan Academy, and I am Dr. Anmol Bhatia. Presently, we are studying the course Applied Thermodynamics, and in that we are doing the topic air standard cycles. Specifically, we will be focusing on Otto cycle in this video.
If you want to study this topic in detail, refer to the book by S-Chan Publishing. Link is provided in the description box.
So the topic is air standard cycles, and we are learning the Otto cycle in this particular video. So what basically this air standard cycle is, and it has particular assumptions. So in basic study of this gas power cycles, we particularly assume that the working fluid is air, and air basically undergo in that particular thermodynamic cycle, even though the working fluid in the actual power system does not undergo a particular cycle. So if there is air inside the particular body, and that particular body undergoes a thermodynamic cycle, and we believe that working fluid there that particularly does not undergo a particular cycle, and in this particular cases we particularly follow certain assumptions, like air that we are using, it continuously circulates in a closed loop, and it always behaves like an ideal gas. So all those ideal gas equations are particularly used in this particular derivations. Then you have the case in which all the processes that makes up the cycles are internally reversible. The combustion process is replaced by heat addition process. So herein we are replacing this combustion of the fuel by adding the heat inside it. And heat rejection process basically restores that working fluid into the initial state, and that particularly replaces the exhaust process. Herein the cold air standard assumptions apply when the working fluid is air and has the constant heat evacuated at the room temperature, which is, let's say, 25 degree Celsius or 77 degree Fahrenheit. So these are particular assumptions in which the major assumption is it behaves like an ideal gas. Okay. Now we'll be dealing with Otto cycle, or we'll be studying with the Otto cycle part. And as you know, that Otto cycle is particularly known as the spark ignition one, in which it is particularly related to the petrol engine. And it has these four strokes: intake stroke, compression, power, and exhaust strokes. So we'll be learning about these particular concepts in this particular diagram. So herein you can see that this is an ideal Otto cycle in which the piston is there, and air comes inside the cylinder. The piston moves upward, which compresses the air, in which we add particular heat, and then the heat is added into it, then it leads to isentropic expansion, in which piston moves from this top dead center value to the bottom dead center. And furthermore, it rejects the heat at constant volume. So when the piston moves from this bottom dead center to the top dead center, the heat is extracted out. So we can represent this with the help of this PV diagram. This PV diagram indicates this particular process, in which you can see that from 1 to 2 there is isentropic compression, and from 2 to 3 the heat is being added. So Q in indicates that the heat is being added. Then from 3 to 4 you can see that there is isentropic expansion, which is this part. From 3 to 4 there is isentropic expansion, and from 4 to 1 the heat is ejected out, or heat is extracted, which is expansion, that is Q out. So you can see that there are two processes, one process which is heat addition process, another is the heat rejection process. and both of them are at constant volumes. So that's why this PV diagram, in this PV diagram, these two lines are the straight lines because it has constant volume processes. But if I talk about the TS diagram, so the TS diagram indicates this value which is of entropy, and that indicates 1 to 2 in this constant manner. Then these two lines, basically 2 to 3 and 4 to 1, these indicates constant volume in this TS diagram. And PV diagram, we already discussed that from 1 to 2 we have this isentropic compression, and from 3 to 4 we have isentropic expansion. That indicates the entropy value is constant. And from 2 to 3 and 4 to 1 we have the constant volume part. So this is particularly related to Otto cycle, having two diagrams. One is PV diagram, another is TS diagram, and the same process is represented by the actual set in which the piston compresses air, then we add heat into it, and then it leads to the isentropic expansion. Now we have the actual 4-stroke spark ignition engine. So this is the ideal case in which you can see the pressure value is up to the fullest or up to the maximum value. But when I talk about the actual part, in the intake part, it has this particular pressure value in which there are differences in terms of pressure. So that pressure, which is the actual pressure which is there inside, that would be reduced, or that would be lesser as compared to the ideal one. And then it has compression, and the pressure value reduces, then the expansion, and then when the valve opens, it has a different value as shown in this particular figure. So this particular diagram, although the shape of this is same, but the pressure and the temperature conditions are no doubt they are reduced to a certain extent. So this is particularly related to the actual 4-stroke spark ignition engine, and this is the ideal Otto cycle case. Now we need to derive an expression for the thermal efficiency of this Otto cycle. Efficiency is particularly related to the output part over the input. So output is what we are getting and input is what we are supplying. So this would be Q input minus Q output over Q input. So whenever this simplifies, it leads to this particular representation. And here when we talk about the 2 to 3 process, that means when we are giving the compression to the particular system, then the constant velocity is there, and this particular thing is related to a law which is the first law, that indicates that the change in this internal energy part is related to the difference between the two, the heat and the work done. So on substituting the values or finding out this W net, we have this W other and WB values, and that particularly indicates that it is 0. So when we substitute this 0 into it, so we get this Q net is equal to the Q input that we are supplying, that is MC delta T part, and we are having two temperatures involvement, which is T3 and T2 here. So T3 minus T2 multiplied by the M and CV, that would be specifically concerned with the input portion. Then the first law, which would be applied to the closed cycle for 4 to 1 process, because in that particular process also the volume is constant. So herein we applied the same first law of thermodynamics as we did for the 2 to 3 process, and also we'll get the value 0 on the similar grounds. And for the output we obtained MC delta T part, but that is specifically related to the expansion. So we'll use a negative sign, T1 minus T4. So negative sign when moves inside, it leads to T4 minus T1. When we substitute this value inside the expression that we had initially, so MCV T4 minus T1, MCV T3 minus T1, MCV and this MCV term can be cancelled out, and we can take this T1 common from here and T2 common from here, so that it can be converted in terms of this constant or the ratio, which is R. So T2 by T1 is equal to V1 by V2 raised to the power K minus 1, because 1 to 2 and 3 to 4 are the isentropic process, and for the isentropic process we had this relationship. And for V3 and V2 or V4, V1 case, the volume is constant. You can check the diagram. For this V2, V3 case, the volume is constant. V1, V4 case, the volume is constant. And from 1 to 2 and 4 or 3, 4 and 3, these two conditions are particularly for the isentropic processes. So for these two part, this temperature values are same, but the temperature values varies in terms of the isentropic process. So what we can do, we have to substitute all these values in the expression, and ultimately we'll get this final expression, which is 1 minus 1 over r raised to the power k minus 1 on substituting these particular values. So this would be the case of the Otto cycle efficiency portion. We stop here for a short break. After coming back from the break, we will learn this concept of Otto cycle with the help of numerical problem.
Now quality learning is easily available at your doorstep. S. Chand Academy brings detailed lectures based on AICTE curriculum as per the New Education Policy 2020. So do not forget to subscribe to the S. Chand Academy and access the wide world of knowledge conveniently sitting at your home. Stay connected and keep watching S. Chand Academy. Happy learning!
Welcome back to S. Chand Academy after the break. I am Dr. Anmol Bhatia and we are learning the concept of Otto cycle. Before going to the break, we have learnt the formula of efficiency which is related to Otto cycle, and we have derived that particular formula. Now applying that particular formula into a numerical problem is a tedious task. So we'll learn that particular concept with the help of numerical problem now. So I'm straight away coming to the numerical problem, and the numerical states that an Otto cycle is having a compression ratio of 9:1. That means you have the value of compression ratio R as 9, and it uses air as a working fluid. So it will be following all those assumptions that we have particularly seen. Now we are given with certain initial conditions, like initially we have P1 value as 95 temperatures and the volume value. Now it is mentioned that during heat addition process, this amount of heat is added, and we need to determine all the T's, P's, efficiency, thermal efficiency, back work ratio, and the mean effective pressure. So all those terms which are required specifically for the Otto cycle, that we need to recall. And assuming that certain values of specific heats are mentioned, like CV is mentioned to us, CP we know, and this constant is there with us, and we need to use this 300K data from this particular table, that is the table, the thermodynamic table, and from there we can generally interpret these values. Now we'll start with the process which is 1 to 2. 1 to 2 process is basically an isentropic process. Before going to the break, we discussed about this particular thing, and we have this value of constant which is 9:1, that is V1 by V2. So we can apply this formula for this isentropic process, that is T2 equals to T1 V1 over V2 raised to the power K minus 1. So this part is R raised to the power K minus 1. On substituting the value, we can find out what is T2. So T2 can be obtained, but keep in mind that we need to convert this temperature value into Kelvins. Now the pressure value, so we'll be using the pressure equation in terms of this isentropic process. So P2 is P1 V1 over V2 raised to the power K. So V1 over V2 is R raised to the power K can be substituted, and pressure we know. So in kilopascal we'll get this value of P2. Now I would be interested in finding out what is the value of the input heat and the output heat. So for that, this Q input, which is MCV T3 minus T2, because 3 to 2 process is that particular process in which we are inputting the amount of heat. So q input is q small q is basically divided by mass, and this mass is v1 over the specific term basically. So v is RT by P. So from there we can calculate the value of this v1, which is the specific volume. So this volume per kg, meter cube per kg, can be determined from there, and we can use this data to get this m value. So q in can be calculated, which is capital Q input divided by m, or you can say that v1 by v. So we have this v1 value, we have this initial volume, and we have input value. So from there we can find out q input, which is the specific value of this heat. Then T3 equals to T2 plus this particular part, which is q input over CV, and from there we can find out this T3 part, temperature 3. So till now we got the temperatures so far. So we got temperature 1 was given to us, we got temperature 2 and temperature 3. Additionally, we are calculating the pressures also. Now you can see, as per this combined gas law, V3 and V2 are same, because as per that particular representation in which we have the constant value of the volume. So from there we can calculate this P3, which is this value, and 3 to 4 is again an isentropic process. So T4 can be calculated from the same expression that we had. Similarly for P4, so all these temperatures and pressures are calculated. Now we are only left with Q out in order to find out the efficiency part. So we can use that same expression, which is mCV minus T1, which is Q out by mass, and then finding out these values, so that this output heat output, which is specific per kg, that can be determined. Recalling that this first law of thermodynamics, when it is applied to the cycles, it leads to W net, which is Q net, that is Q input minus Q output. So we can find out this W net, which is the subtraction of the two. And on dividing these two values, which is the output value and the input value, I can obtain this thermal efficiency of this Otto cycle. Additionally, if mean effective pressure is required, so we can use this formula, W net over V max minus V min. So per mass we can calculate, so W net over V max minus V min. So these values we already have, but we can convert these values in terms of that constant, and that constant is R. So W net over V1, 1 minus 1 over R. We can substitute all these values so that a final result can come out, and that would be the mean effective pressure. And ultimately, if I talk about this back work ratio, so back work ratio is an important term, and it has a formula presentation, which is the compressive work, or you can say the work which is involved during compression to the work which can be done during expansion. So during compression you can see that the process is 1 to 2 for compression, and for expansion the process is 3 to 4. So from there you can put in the formula like MC delta T's formula. So CV T2 minus T1 and CV T3 minus T4 values. You have the value of all these temperature conditions. On substituting the temperature conditions, you will get this back work ratio part. So as of now, we understood how can we calculate all these temperature values, all the pressure values, and the thermal efficiency, additionally the mean effective pressure having a particular formula, and the back work ratio part. With this, we come to the end of this video, wherein we learnt about the air standard cycles, which is specifically the Otto cycle. We derived the expression for the Otto cycle, and we analyzed the same with the help of numerical problem. Thank you.
If you want to study this topic in detail, refer to the book by S. John Publishing. Link is provided in the description box. If you found our video interesting, please like, share and subscribe, and press the bell icon for future updates.
All rights reserved.
This video has been prepared for educational purposes only. No part of it may be reproduced or copied without the permission of the copyright holder.